Great. It is my pleasure and honor to welcome Bram Mesland from the Netherlands, University of Leiden. And in principle, his talk will be about equivariant spectral triples. It's all yours. Take it away.
It will be a very principled talk. Yes, so I will indeed contribute to this kickoff meeting by explaining this work package, and as requested, I will spend quite some time on reviewing some recent work, and then present some of the natural questions that that arise when you look at what we've done here. I also saw that my collaborator Bram Mesland is in the audience, and I know he has been actually already doing some work in some of the directions I will mention. So Bram, if at any point you want to comment, feel free to do so. All right, so yes, I will be talking about the setup of non-commutative differential geometry, as I often do, which takes the C-star algebra picture as a non-commutative topological space, but then consider some finer structure, which is often done via spectral triples, can also be done by just specifying some Fréchet subalgebras or things like this. For simplicity, I did not write this, but whenever a space or a C-star algebra appears, for the moment, unless I say differently, let's just assume that things are compact and unital. Even though we can do various things in the more general non-unital setting, the complications introduced are mostly of a technical nature and not very essential. So that's a disclaimer. Well, principal bundles we saw already, I think, in various talks, and we know they are a central notion in geometry and physics. And I just want to review the classical setup where, again, fairly simple. G is a compact Lie group. P is a compact G space on which this group G acts freely and therefore automatically properly, with a quotient space P mod G. And then the natural C-star algebras are the continuous functions on P and the continuous functions on B, which can, in this case, be viewed as the fixed point algebra of this action. Now, the quotient map pi in point 4 here is then a smooth Riemannian submersion, and as such, it induces a wrong-way map in K-theory, which often has interesting properties. And this map pi shriek is actually induced by a specific class in the Kasparov K group that goes between C of P and C of B. Okay, so this is the classical structure that is very well understood and always there. And what we did in recent work with Branimir was abstract this to a general G-C-star algebra A. So what we've done so far, and what I will spend most of my time here explaining, is, okay, we've made the total space non-commutative of the principal bundle, but we left the structure group to be classical and even compact, as you do in first steps. So a definition that's been around for a long time, and there are various quantum group versions of this definition as well, is that a C-star algebra's principle, if this map here, which goes from A tensor A into the continuous functions of G with values in A, given by sending a tensor A1, tensor A2 to the G value, to the function that takes its values on G by letting the group act on the first algebra element and then multiply it with the second one. And the requirement is then that this map should have dense range, and that turns out classically to be equivalent to the freeness of the action of G, all again very well known. So if CP is a principal C-star, G C-star algebra, then the action of G is free. So
But yeah, G is compact, right?
Yeah, G is compact, so there are no complications with properness. And so the only issue to have a principal bundle is the freeness.
Yeah.
And so this gives us a notion of topological principal bundles. And now we want to extend this, and that's the main content of our work, to the spectral triple setting, where we want to include the differential geometric structure. So just to most of you recall this well-known definition. So a G spectral triple AHD consists of a graded Hilbert space. So I just wrote this out explicitly. It means that the Hilbert space consists of two pieces, H plus and H minus. And the pair A comma G, so A is a G-C-star algebra, but we now require that we have a representation of both A and G that is covariant in the usual way. So meaning that if we conjugate an element of A by now a unitary that implements the action of G, then we actually see the action on A. And then we have an operator D, which is closed and G invariant, and it swaps the Hilbert spaces in the grading. And now I said from the start that my algebras would be unital, so the requirement that A times 1 plus D squared inverse is compact would just reduce to the requirement that 1 plus D squared inverse is compact. And then the dense subalgebra, which I specify here in the spectral triple, should be such that the commutators of D plus and D minus are bounded. So I wrote it only for D plus, but since they are mutual adjoints, it follows for D minus then as well. I'm also assuming the representation of A is so with this data, again, well known, we get an equivariant K-homology class. And because everything is nicely equivariant, we can take the fixed point algebra, the fixed point Hilbert space, and the invariant operator, and this gives us another spectral triple on the fixed point algebra. And this inclusion of the fixed point algebra into A can then be viewed as the analog of the principal bundle map. So that's the setup here. And now we want to realize this principal bundle map in a non-commutative differential geometric setting. So that means, as I said before, this in the commutative case, this pi induces a streak map, which is a certain KK element. And so we have to think a little bit about KK theory. I will keep this mild, but just recall the basic structure. So Kasparov introduced the bivariant KK groups in such a way that, well, we have two C-star algebras, we get an abelian group, KKAB. And if we insert the complex number C in the first slot, we just get the K theory. If we insert the complex number in the second slot, we get the K homology of A. And the main feature of this theory is that there is this kind of categorical structure, which is the Kasparov product, which allows you to compose elements in different KK groups as soon as the first and the last argument of both group match up. And this recovers, for instance, the familiar index pairing by restricting Kasparov product to the KK groups of C, A and A, C. So what's important here is that as soon as I get an element in a KK group, so that's in the second to last dot here, then I get a map between K theory and K homology groups. And the idea is now that in non-commutative differential geometry, you should be able to lift this topological data, because this map is topologically defined. KK theory is a topological theory. You should define it to a refined representative of this element in the KK group that is in some sense geometric, and that we then think of as representing the morphism or the smooth bundle map in our case. So we want to look at cycles for KK theory, but let's give a little bit more motivation for this picture that I just sketched, because in the early 80s, Kohn and Skandales gave this kind of geometric interpretation for the KK theory of commutative algebras by introducing what they called a geometric correspondence. So we need some finer structure. This is again the spirit of the game. We compute topological invariants, but we work with differential geometric objects. So M and N are compact manifolds. Then a correspondence is a diagram sketched here, which in the middle contains another manifold Z and a vector bundle on that manifold, and then two maps out of Z. So from Z to M, that is this F, and from Z to N, that is this G, which satisfies some regularity conditions. So F should be smooth and proper, which if everything is compact is a mild condition. And G needs to satisfy a spin C type condition, which is called K orientation. I will not go into the details of that. And Kohn and Skandales showed that if any element in the KK group associated to two manifolds can actually be represented by such a correspondence. And the Kasparov product, which in the general analytic picture that Kasparov gave us is notoriously difficult to compute explicitly, can actually be realized up to some equivalence notion called transversality by just taking the fiber product of two of these correspondences, as I've written out here at the bottom of the theorem. So you take the fiber product of the spaces Z1 and Z2 and basically the tensor product of the two vector bundles that you have there. And so this adds further credibility to this point of view that in fact, KK theory is really given by homotopy classes of generalized smooth maps. So now back to this non-commutative picture. If we have a spectral triple, then what we get for free from that, if we have BHD, and recall that the curly B that I specify here is always an algebra which has bounded commutators with the operator D, we get a natural module of one forms, which is the space indicated here. So, and this is inspired by the fact that if you take a Clifford module on a Riemannian manifold, or if you have a spin structure, then this module that you get, because the commutators with the Dirac operator are really a representation of the space of differential one forms, you really get a module that is naturally isomorphic to the differential one forms. And
Bram, can I ask? Bram,
yes.
Can I ask you? So that's the closure of the linear span. I understand why you need it. Usually you don't. Why you need to make a closure of this one forms?
Well, because I want this space also to have some analytic structure. So in general, on a manifold, you know that this module is really the module of differential forms, and so it's nicely finitely generated and so on. In the abstract setting, you don't know very much about it, and you need to sometimes address convergence questions. So if you take this closure in classically, you get basically the continuous one forms, so to speak. So you, or another way to view it is what you get is you just take the bundle of differentiable or smooth one forms, then this closure will just give you the closure that you get by induced by the inner product coming from the Riemannian metric. So classically, you just get the natural Hilbert module that is given to you. Okay. So you don't really introduce anything extra there. It's for analytic technical reasons I need to do this.
Thanks.
All right, so B, the curly B indeed here, as mentioned, is some dense star subalgebra. And if we want to think about geometric structures, I want to consider some very weak or some non-closed modules. So my curly X here I want it to be a pre-C star module. So it's a right B module, and there is an inner product satisfying the usual axioms, such that if I take the completion in the C star module, in the C star norm on B, I get a nice C star module. But a connection that I now want to think about is a map that is defined only on this dense submodule. And here you see that the connection, the domain of the connection is the sort of the differentiable module, but the codomain involves the C star closure and also the closure of this modular forms. And the connection should satisfy some kind of Leibniz rule. And then it turns out that if you have two spectral triples, you can make sense of the notion of differential correspondence, which is the non-commutative analog of these Kohn-Skandalis correspondences. And that's a triple X as nabla, where X is one of these inner product modules, S is some unbounded operator on it, so a differential operator that acts as modular endomorphisms, and nabla is a connection. And if you have this data, then you can form modulo some analytic conditions, which I'm further wiping under the rug here. You can form explicitly the Kasparov product in the way indicated here. And we say that X as nabla is a correspondence between the two spectral triples if this explicit Kasparov product is equivalent to the original second spectral triple modulo some reasonable perturbations. We will in the example see what this can possibly be. So our goal is now for a principal G spectral triple to construct a differential correspondence between the total spectral triple and the fixed point algebra. And so we need to find a module, an operator, and a connection. So the module is in some sense the most straightforward part. So there is, of course, because we have the G action by a compact group, there's a nice conditional expectation, and this is a completely positive map, and you can construct, you can use this to construct an AG bimodule, which I denote by L2V of A, where the V stands for vertical. If you would look at the paper where this is described, then it looks all slightly more complicated there, because you need to also take into account the relevant Clifford structure. And that's also in order to get this operator that I've written here in the middle of the page. So you get a natural operator on this module by fixing an ad invariant inner product on the Lie algebra, and you choose a dual pair of bases, and the rho is another piece of data that is the vertical Riemannian metric. And the existence of all these structures needs to be, is quite important input into the final result that we get, because you will not be able to always find these things, because there may be an obstruction to the factorization result. But if you have all these structures, then the data L2 vertical of A and this operator S, it defines a KK cycle for the two algebras. But note that there is no connection yet. But this cycle exists in a great deal of generality. And the connection, for that you need to require some analytic analog of the notion of strong connection that has been around in the more algebraic literature for a long time. And because in the definition here of the correspondence, we cannot really expect to find the spectral triple as a product on the nose. There will always be perturbation terms, and that's encoded here in this definition of a strong remainder, which is an odd G invariant operator Z on H, such that if I take the difference of the total D with the vertical D and the Z, and I take commutators with A, then I actually land in the algebra forms for this second operator. And this you can only expect to happen once you subtract this Z. So this is something you need to look for. And once you have this, then you can actually quite naturally make a connection which is densely defined. And by equipping the vertical module with this connection, you find that you get a nice differential correspondence. And so this all works for any principal GC algebra A satisfying some of these extra geometric conditions that are wiped under the rug. But there is quite a structural machine here. And the result we have there, it applies to all classical principal bundles, which could even be non-compact. So I have not discussed this, but we can actually deal with non-compact bundles. And our results are also stable under theta deformation. So we can deal with, for example, the theta deformed 7 sphere over the theta deformed 4 sphere, which has this non-abelian fiber SU2 actually. I've written S3 here, which is maybe from a group perspective not that natural. And also cross products by Zn can be dealt with. It's important to note here, so one effort that needs to be made is you need to always start from a spectral triple on the total space. So there are many algebras for which natural spectral triples are not always available. So part of the research that we will be doing is to find natural spectral triples, for instance, on quantum groups that satisfy these nice principality conditions and that we can then factor. And of course, in line with the theme of this grant, is an important effort will go into constructing more examples, such as Kunz-Krieger and Graf-Sister algebras, which carry, well, at least the Kunz-Krieger algebras carry natural gauge action by U1. Probably graph algebras do too. And there it's already known that you cannot, depending on which spectral triple you choose on a Kunz-Krieger algebra, you cannot always expect that it will factor over this fixed point algebra. So there are conditions to be investigated there. And then, of course, a lot of the harder work will go into replacing the group G by a quantum group. This would make the setting truly non-commutative. And also the use of non-compact structure groups presents various challenges because our work for the compact case depends very strongly on the Peter-Weil theorem that you have available for representations of compact groups on Hilbert modules. Of course, if you drop the compactness, then the representation theory becomes much wilder. Fully developed non-commutative gauge theory, which we also made a start with already. And something I did not write is study curvature invariance associated to the connections that you see here. And as mentioned before, construct more examples. That's actually one of the main efforts. So I see that I am quite fast through my time because this was my talk.
Okay, thank you very much. So now we have plenty of time for questions. Any volunteers? I'm looking for some raised hands. Branimir, how about you weighing in? That's also your baby. Hello, Canada.
Yeah, greetings from Fredericton. Yeah, so I mean, there's a lot that one can do here. One of the things that we worked out is also you can talk, because we allow the vertical Riemannian metric to have non-trivial transverse dependence. There's a fully worked out theory of sort of shape operators and talk about, do you have totally geodesic orbits? Are they totally umbilical, et cetera, et cetera, et cetera. The other thing I would also point out, and this is sort of slightly shameless self-promotion, but if you start thinking about circle bundles, in the case of circle bundles, it's quite pertinent, is obviously very pertinent to this whole project. You can, the moment, like what I want to say is this, the moment you're not dealing with a compact Lie group with the de Rham calculus as your structure group, things can go very wrong very quickly. So if you want to think about something like, for instance, the non-universal Q monopole, which is a circle bundle with a Q square deformed structure group. I think I've recently proved that you can't even accommodate this in the framework of twistor spectral triples. You have different things happen in the vertical and horizontal directions. So one thing we'll need to be prepared for, even just looking at what ought to be just bog standard circle bundles, is there could be some modular weirdness appearing of a geometric nature. Not like usually think, modularity comes from non-commutative measure theory, but in this game it can come from it can have a geometric origin actually. So that's what that's maybe the main thing I want to point out.
Well, I noticed in your very recent paper that you had, but this must be related, but I have of course not digested everything yet, but you had some kind of no-go result regarding SUQ2.
Yeah, it's I mean there's various things you can say in general. For starters, like Schmidtgen had this sort of no-go result back in the day. And for starters, the moment you have a quantum principal circle bundle with connection whose structure group is U1 not with the de Rham calculus, but with some sort of Q deformed calculus. So dz times z is q z dz, or q not equal to 1. You cannot faithfully represent this in terms of a a bounded commutator representation. So that basically rules out ordinary spectral triples. Yeah. But now then next you can ask, okay, can I get away with a twisted spectral triple? Can I sort of damp unboundedness of my represented one forms in one go with a single sort of modular operator? And sort of what ends up happening there is, if you're really careful with analyzing the geometry of your quantum principal circle bundles with connection, basically typically what one expects, and this is actually hard and fast and unavoidable in the case of the Q monopole, and similar examples where the base algebra has centered the scalars. What typically happens is that you like vertical represented one forms, represented vertical one forms, and represented horizontal one forms will be unbounded in different ways and require fundamentally different dampings. Which means that you cannot, which means that you can't even get away with a twisted spectral triple, because you need, so for the Q monopole you need powers of Q squared. Like basically the unboundedness of vertical one form for the Q monopole is necessarily like powers of Q squared, whereas for horizontal one forms it's necessarily like powers of Q. Right. So we're really at the boundary of sort of non-commutative Riemannian geometry as we know it.
But and do you think that so you're saying we need to develop new concepts to accommodate this, or is this the end of it?
Well, one of the curious things is that, and this is sort of, I guess, leading in probably to the next talk, is that, believe it or not, there are no obstacles to quantum metric spaces. Because so there is this recent preprint of Kad and Kied about the Q about quantum SU2. Yeah. And when you take the choice of parameter t equals q squared, which corresponds basically to the Voronovich's 3D calculus, that regime up to equivalence of semi-norms can be generalized. That Lipschitz semi-norm can be generalized, and you can make sense of it without invoking twisted commutators. You can make sense of it without breaking the relation to the differential calculus. But of course, the quantum metric space doesn't require easily accessible index theory. It's its own separate direction. So I'm actually quite optimistic that a lot of what Kad and Kied do can be generalized quite extensively. I'm very optimistic in that regard. But for the index theory, I mean, that's a puzzle. Yeah. I mean, you like, how the hell do you extract index theory out of gadgets where
your one forms are behaving wildly differently in different directions. That's undiscovered country. I have no idea.
So there's a lot to do.
Yeah. The one other thing that comes to mind, though, is that, I mean, like, if I'm sure a lot of people have seen Biggs and Majid's monograph on quantum Riemannian geometry, and I think it's a good reminder that there's a lot you can do just from starting from the ground up and thinking about your differential graded algebras. So I think there's a lot of fun to be had with just thinking about Leavitt path algebras and just starting from scratch and saying, okay, what do nice DJs over these things look like? Is there something natural one can do in terms of the graphs? I think that there could be a lot of fun sort of starting really at the ground and working your way up in terms of structures. And I mean, if you get an theory out of it, great. If not, well, it's more evidence. I mean, already something as fundamental as the Q monopole is, outside the bounds of ordinary twisted spectral triples. So, I mean, we need more data to see where to go next. I don't know. That's my little spiel.
Right.
Okay, thank you very much. Anybody else? Andre, how about your spectral triple perspective on?
Well, the spectral triple perspective, well, there are a couple of things, because spectral triples sometimes do require not require, sometimes allow for more structure than only Dirac operator. So this is something. I mean, here what one gets from what I understand, I mean, this is still the problem of constructing, going the other way around, constructing the Dirac operator from the Dirac operator on a base space. And on a fiber is something that's a challenge, still a challenge, right?
In some sense, yes, because there are various factorization results already completely commutatively, where you see that the natural Dirac operator on the big manifold, that you cannot get it at least not as a straightforward construction by just adding a connection term. Because there is curvature information that obstructs getting it directly. So you get perturbation terms that encode some, basically the curvature of this principal bundle, or of the Riemannian submersion at hand. And this seems, to me at least, to be extraneous information that you cannot expect to be put in beforehand, which is which I mean, and in that sense you're touching upon this problem that Branimir also mentioned, like, how do you know when you what is the right spectral triple to look at on the total space? If there would be a nice procedure to just lift it from the base, then that would be very helpful, but it looks like.
So just to emphasize what Bram said, sorry, our result is top down. You start at the total space, and you work your way down, and you sort of factor the total space such as it is, and there's actually a canonical candidate for this remainder term involving curvature information. What's actually interesting is that when you take U1 with the de Rham calculus, this canonical remainder, this is basically this basically recovers what Anja, you and Ludwig got in your CMP paper on circle spectral triples. Yeah, so you had this canonical vertical, canonical horizontal, and this d minus dv minus dh, which you could write down even when the lengths of your fibers varied, and that remainder, like that's the canonical guess. So there's actually a canonical guess that involving curvature information. It'll be a mixture. So you can write down your mean curvature one, the mean curvature one form, this extrinsic curvature of the fibers. You can write this down in general and subtract it away. And what you'd be left with is, like, there's some principal curvature stuff, and there's some moment information like that's morally the difference between Lie differentiation along your Lie action and covariant differentiation in the vertical direction.
Yeah, but the question is, how do you access this kind of information in a completely abstract non-commutative system? This is often unclear, I think. So you can lift often operators, but the geometry that they would then describe is often not the correct one, because you would miss these error terms. So as I indicated, a lot of the work that needs to be done in this direction to get more non-commutative examples will actually consist of constructing good spectral triples to begin with.
So in the circle case, if you really want a sort of canonical picture of how to formally live, that's worked out in my preprint, and it's consistent with sort of Hodge-Durham type situations coming from sort of Riemannian structure in a very sort of narrow sense. But then the problem, but then you run into these difficulties. You do everything as natural as possible, starting from the ground up. But this comes at a price. Like you run into these sort of pick 2 out of 3 situations where, if you respect the differential geometry, you don't have a meaningful twisted spectral triple even. So, and that's sort of what's puzzling about the Q monopole. It's really one of these sort of like meme, like, you know, pick 2 out of 3. You can have something resembling a twisted spectral triple, or you can have you can always have a compact quantum metric space, basically by Cauchy-Quied, for any reasonable choice. But then you have to choose: do you want the geometrically natural, quantum principal bundle that, which requires the Vodonovich's 3D calculus, or do you want something formally that's a twisted spectral triple? You can't have both.
Yeah.
And in particular, the only way, like the Vodonovich's 3D calculus, like that's kind of forced upon you too, because the moment you treat the centered Polish sphere as a 2-manifold with Podlush's calculus, which is the unique covariant blah 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 to classical dimension calculus, and the moment you want to then treat the Q monopole, these associated connections as constant curvature connections, you have no choice. The Vodonovich's 3D calculus is forced upon you. But then Vodonovich's 3D calculus gives you something with wildly different behaviors in the vertical and horizontal direction. So,
Let me ask you a very naive question. So what happens if your principal bundle is trivial? If you just have a cross product, do things become much easier? They should.
well,
Then yeah. Well,
they do become easier for the most part, but again, even if you're just dealing with a single automorphism and take a cross product by Z, think of this as a circle bundle.
Yeah.
The moment you're not essentially isometric, the moment there's, for instance, non-trivial conformal behavior, you're going to have to do something funny in the horizontal direction. There's going to be some non-trivial damping involved.
In that sense, yeah.
So even in the trivial case, the moment there's so that's one of these sort of geometric sources of sort of modularity. It's basically conformal behavior.
Okay. And can you show me again the slide with a list of types of principal bundles that you can handle?
Yeah, so
classical, yes.
Yeah, classical theta deformations, and we cross products by Zn.
Under a sort of metric equivariance.
Yeah,
condition.
Of course, there are always conditions here. I really do suspect that certain Kunz-Krieger algebras, for example, can also be handled, but somehow not all of them. We've seen this some time ago already, that the class that you get from the circle action, so the KK class that goes to the fixed point algebra, it can be 0, for instance, and then you cannot expect to have a factorization result if your original spectral triple is not 0. So there are these topological obstructions sitting there as well. But I expect that in this Kunz-Krieger and maybe also more general graph C-star algebra cases, it should be possible to write down some reasonable conditions under which this should be possible.
And when you say this should be possible, what exactly you have in mind?
Well, this kind of factorization result.
Okay, factorization.
That you can write your equivariant spectral triple as a product of some natural, in this case, U1 induced cycle coming from the gauge action, tensored with a spectral triple on the fixed point algebra of this gauge action.
Mm-hmm, mm-hmm. And how is graph structure supposed to help it?
Well, this I don't know yet. I just know that there are examples of Kunz-Krieger algebras where we know that the class, the KK class that is defined by this circle action is vanishing. So in those cases, you cannot expect to get a factorization result, because if your original spectral triple has a non-zero class and you factor it as a Kasparov product with something that's 0, then that's not possible, right? That's like a topological obstruction. So what needs to be investigated here is that there should be some conditions on the underlying graph, probably, that would tell you when this obstruction is there or not.
Mm-hmm. Okay, that sounds very concrete.
Yeah.
Yeah. David, any comments or questions? Ludwig, you're also a spectral triple guy.
Well, yes, but we remained with Andrzej on the level of U1 on circle actions, but that's of course much more complicated stuff and much more advanced. And
well, but as Branimir indicated, already for circle actions there are problems.
Yes.
I mean, well, actually, one comment I might make might be helpful in sort of interpreting this sort of. Bram, could you go back to the unbounded KK cycle, S?
This
So
one?
yeah, I mean, either is okay. I mean, a good way to think about or maybe the last one, the one just before it.
Definitions, yeah.
Yeah. So a good way to think about your A curly X S nablas. I think this is a picture. Let's go maybe back to Denis Perrault. Like you can think of this curly X curly S as like a family of spectral triples, parameterized non-commutatively by curly B, and then nabla is a connection for this family of spectral triples. And so you can think of S and nabla as together forming like a Quillen superconnection, non-commutative superconnection for this family of spectral triples. So it's really giving you fiber-wise geometry. So on the next slide, this S, that you're getting, like this is Costin's cubic Dirac on each of the fibers. And it's actually very useful to specifically model this thing on Costin's cubic Dirac. Like it really gives you huge computational advantages.
Well, I'm certain, Bram, that you mentioned it, but could you please repeat it for me? Where exactly it's crucial that you have this freeness, this principality? At which stage do you use it? I'm sure you explained it, but I would like to memorize it.
Well, to get this class on a KK level, you need the principality.
Okay.
The principality means that the isotypical components are FGPs.
Yeah. Oh, yeah. That's a very good way of saying it. So there is this. Yeah.
So sort of local triviality dimension aside, the moment you have this principal action, actually quite generally, I guess, for results of De Comet and Yamashita, like there's a sort of vestigial local triviality that still persists where all your non-commutative associated vector bundles remain FGP.
Yeah, so this is kind of this Peter Weil type theorem that is then available. Well, it's not, it's available, but it's, as Branimir said, it means that the components in the Peter-Weil decomposition become FGPs, and this you need to prove that your vertical operator has a compact resolvent in the module sense.
Yes.
So that's where this is crucial input.
Yes. Now I appreciate it, because in fact, to prove our theorem that you have a free action of a compact quantum group if and only if its Peter-Weil Hove algebra acts in a principal manner. This is exactly the way it's done is precisely by proving that these components in the Peter-Weil decomposition are finely generated projective. This is the most difficult technical lemma.
Exactly.
Which was proven by Kenny DeComber and Koto Yamashita.
When we were doing our work, we were very happy to find this result, so we didn't have to do that work ourselves.
And you can finesse it a little bit when A is non-unital too. Like there's a good enough, like countably something. There's a good enough.
Yeah. For non-unital A's, I can imagine. What is really scary is non-compact quantum group. That's definitely. Okay, guys, the time is up. Thank you so much. We have 4-minute break, and then cherry on the cake, David Kidd. But I stop recording now and resume in 4 minutes.
All right, thank you.